This is a video from section 4.6 in linear algebra. The directions say to find a basis for the solution space of the homogeneous linear system. Find the dimension of the space. In problem 1, we're given the following linear system. x1 plus x2 minus x3 equals 0. Negative 2x1 minus x2 plus 2x3 equals 0. Negative x1 plus x3 equals 0. So what we're going to do is we're going to set up the augmented matrix for that system. And that consists of the following entries. In the first row, we got 1, 1, negative 1, 0. In the second row, we got negative 2, negative 1, 2, 0. In the third row, we got negative 1, 0, 1, 0. And so we're going to perform a series of elementary row operations to get this in row echelon form. So I'm going to take 2 row 1, add it to row 2, put the result back into row 2. Take row 1 plus row 3, put the result back into row 3. And so I get the following matrix. In the first row, we get 1, 1, negative 1, 0. In the second row, we get 0, 1, 0, 0. In the third row, interestingly, we get 0, 1, 0, 0. And so I'm going to take negative row 2, add it to row 3, put the result back into row 3. And when that occurs, we get the matrix 1, 1, negative 1, 0, 0, 1, 0, 0, 0, 0, 0, 0. So my system looks like the following. x1 plus x2 minus x3 equals 0. That corresponds to the first row of entries. x2 equals 0. x3 is my free variable, right? So I'm going to let x3 equal t. And so that tells me x1 is t. Because remember, x2 is 0. I'm going to replace x2 with 0 in the first equation. And when I do that, x1 equals x3. And so if x3 is t, x1 is t. And so therefore the column vector x1, x2, x3 is equal to the column vector t0, t, which is equal to t times the column vector 1, 0, 1. The basis for the solution space is the column vector 1, 0, 1. And there's only one vector in that space. And so the dimension is 1. Let's take a look at 3. Suppose I'm given 2x1 plus x2 plus 3x3 equals 0. x1 plus 5x3 equals 0. x2 plus x3 equals 0. Setting up my augmented matrix, I get the matrix 2, 1, 3, 0, 1, 0, 5, 0, and then 0, 1, 1, 0. So I'm going to take row 1 and interchange it with row 2 so I can get a leading 1 in the first row. And when I do that, I get the matrix 1, 0, 5, 0, right? That is the interchange, right? And in the second row, I get 2, 1, 3, 0. And the third row is 0, 1, 1, 0. So the third row didn't change. And so I'm going to take negative 2 row 1, add it to row 2, put the result back into row 2. I want row echelon. You can do reduced. That's fine. And so I get the matrix 1, 0, 5, 0, 0, 1, negative 7, 0, 0, 1, 1, 0. And so I want to use row 2 to turn this entry into a 0. And I'm going to do that by taking negative row 2, add it to row 3, put the result back into row 3. And so on the next matrix, I get 1, 0, 5, 0, 0, 1, negative 7, 0, 0, 0, 8, 0. And I want to turn this entry here into a leading 1. And when I do, I get the matrix 1, 0, 5, 0, 0, 1, negative 7, 0, 0, 0, 1, 0. And now we're in row echelon form, so this is good. Now notice that x1 plus 5x3 equals 0. x2, looking at the second row, minus 7x3 equals 0, and then x3 is 0. If I solve, you can hopefully see that x1, x2 both have to be 0, right? x3 is already 0. And so if I solve for x1 and x2, you're getting 0. And so therefore there's no basis for the solution space, because the only solution is the trivial solution. And so therefore the dimension is 0, because the only solution in that system is the 0 vector. Number 4. Now in this one, we have the system x1 minus 4x2 plus 3x3 minus x4 equals 0. And then 2x1 minus 8x2 plus 6x3 minus 2x4 equals 0. And so my augmented matrix is 1, negative 4, 3, negative 1, 0, 2, negative 8, 6, negative 2, 0. And I'm going to take negative 2, row 1, add it to row 2, put the result back into row 2. And when that occurs, I get the matrix 1, negative 4, 3, negative 1, 0, 0, 0, 0, 0, 0. And I'm done. So notice, x1 minus 4x2 plus 3x3 minus x4 equals 0. That's the only equation I have. So I have 3 free variables. 3 free variables. And so what I do is I let x2 be r, x3 be s, and x4 be t. Solving for x1, I get 4r minus 3s plus t. And so the column vector x1, x2, x3, x4 is equal to the column vector 4r minus 3s plus t, rst. And I'm going to split this off into r times the column vector 4, 1, 0, 0 plus s times the column vector negative 3, 0, 1, 0 plus t times the column vector 1, 0, 0, 1. And so therefore, the basis is the set of column vectors 4, 1, 0, 0, negative 3, 0, 1, 0, and then 1, 0, 0, 1. The dimension of that solution space happens to be 3. And that's how you do problem number 4. If we can, let's take a look at problem number 6. Suppose I'm given x plus y plus z equals 0. And then we get 3x plus 2y minus 2z equals 0. And then we get 4x plus 3y minus z equals 0. And then we get 6x plus 5y plus z equals 0. So I'm going to set up my augmented matrix. In the first row, we get 1, 1, 1, 0. In the second row, we get 3, 2, negative 2, 0. And then we get 4, 3, negative 1, 0. And then we get 6, 5, 1, 0. Now, there's a series of 3 elementary row operations we can do. I'm going to take negative 3, row 1, add it to row 2, put the result back into row 2. I'm going to take negative 4, row 1, add it to row 3, put the result back into row 3, and then I'm going to take negative 6, row 1, add it to row 4 this time, put the result back into row 4. And let's see what happens. Now, if you notice, the first row doesn't change. You get 1, 1, 1, 0. In the second row, we're going to get a 0, right? And then if I take negative 3 plus 2, I get negative 1, right? Let's make sure we understand that. I'm taking negative 3 times that entry and adding 2. Okay? And then that's negative 1. And then negative 3 plus negative 2 is negative 5. And then I get a 0. And then I get a 0 by design, right? And then I'm going to go negative 4 times 1 plus 3. That's negative 1 again. And then I get negative 5, 0. And then I get a 0, right? And then I'm going to get, again, and then negative 6 plus 5 is negative 1, and then negative 6 plus 1 is negative 5. And so I get negative 1, negative 5, 0. This one's really interesting. Okay, now, if we don't mind, I'm going to take negative row 2, add it to row 3, put the result back into row 3. And then I'm going to take negative row 2, add it to row 4, put the result back into row 4. When I do that, I get the following. I get 1, 1, 1, 0, 0, negative 1, negative 5, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay? And then one last step, I'm going to take negative 1, row 2, put the result back into row 2. And so I get the matrix 1, 1, 1, 0. And then in the second row, I get 0, 1, 5, 0. 0, 0, 0, 0, 0, 0, 0, 0. And then from here, x plus y plus z equals 0. And then y plus 5z equals 0. Okay. I hope that's okay. So z is free, so I'm going to let z equal t, right? Because there's a leading 1 in the first column, and there's a leading 1, well, in fact, there's a leading 1 in the first row, and there's a leading 1 in the second row, but no leading 1 in the third or fourth row, interestingly, right? So I'm going to let z be t. Y is equal to negative 5t. And then x minus 5t, making my substitution, plus t equals 0, so x is 4t. So I'm going to get x, y, z. So the column vector x, y, z, as I was saying, is going to be 4t, negative 5t, t. And this is t times the column vector 4, negative 5, 1. So the basis for the solution space is the column vector 4, negative 5, 1. What's the dimension? The dimension is 1. Okay, that'll do it for this video for section 4.6, and we looked at problems 1, 3, 4, and 6. Thank you.